Welcome, everyone. For today's prep, we're going to look at one more application of definite integrals for now, and that is calculating the length of a curve, calculating the arc length. So again, this is going to be another application of definite integrals. So let's get to the main result here, the star of the show. And we have this curve y equal to f of x. We're only going to be looking at a section of it, so an interval for x here is specified. X is between a and b. And the length of that section of curve is going to be the integral from a to b of the square root of 1 plus the derivative of our function squared with dx at the end. Now there is a little requirement here in order for this formula to work, and that is we need that derivative f prime, or dy dx. We need that derivative to be continuous on this closed interval. All right, so this formula, as it's written, is when our function is defined in terms of x. So x here is the kind of the main variable for our function. So we just want to be careful when we actually set up the integral. We should have a dx at the end if we're kind of setting it up this way, where x is the main variable. So just kind of keep track of your differentials here. Now we will also look at curves where maybe they're not written exactly like this. Maybe they're not written as y equals. Maybe they're written as x equals, and there's a very similar formula. So we'll also see if we have a curve given in the form x equal to some function of y, where y is going to be our main variable, and we have an interval for y, maybe let's use c and d, where y is between c and d. So again, we're just looking at a section of our curve here over some interval. Well, then the length in that case is going to be the integral from c to d of 1 plus the derivative of x with respect to y squared, and then dy at the end. So again, we just got to pay attention. If y is the main variable of our function, well, when we set up our integral, we should have a dy at the end. All right, so where does this function, or where does this integral formula come from? So it might, it's not necessarily intuitive where this is coming from. Square root of 1 plus the derivative squared. Well, let's look at a little. We're not going to prove this, but we're going to look at the idea for how the proof would work. So let's look at the idea of the proof. So let's start with a curve. So let's say this is our curve here. And we're interested in just figuring out the length for just a section of this curve, going from, x equals a to x equals b as the other endpoint. So we want to know the length here. How do we do it? Well, our idea is to kind of take that curve and break it up into a whole bunch of tiny little pieces. So let's maybe something like that. So I've broken that whole line segment up, or that whole curve up, into how many little pieces? We got 1 piece, 2 piece, 3 pieces, 4 pieces, 5, 6, 7, 8. So 8 pieces here. So I've taken that whole curve and I've broken it up into 8 pieces. Now the idea is we're going to use smaller and smaller pieces, but more of them. But for right now, let's kind of zoom in on just one of these little sections here. So let's kind of zoom in on this section here. So we have our 1 point, we have our other point, and then we have our curve kind of connecting those 2 points. And what we want to do is we're going to kind of approximate that section of our curve with essentially a tangent line. And now that this is a straight line, we can figure out the length here by, well, a little bit of geometry, a little bit of right triangle usage. So we can look at the vertical height, and then we can look at the horizontal height or distance. And this forms a right triangle. So the horizontal distance, that's change in x. Vertical distance, change in y. And then we have this hypotenuse here. And, well, it's a right triangle, so we can figure out the length. And the length of that is going to be, and let me get out of the way. There we go. The length of this is square root one side of our right triangle squared, so the delta x side squared, plus the other side squared, length of the other side squared. Now, the idea is, now you can kind of see where this square root's coming from. It's really coming from the Pythagorean theorem. Well, let's factor out a little bit here. So I'm going to factor out a delta x squared from this term and from this term. So when I factor out that first term, I'm just going to have a 1 left. And then in my second term, I'm going to have delta y over delta x squared, and then this whole thing times delta x squared. So again, you can kind of check, if I were to take delta x squared and I were to distribute it back in, when I multiply it with the 1, I get my delta x squared, and then when I multiply it into this fraction, the delta x squared down here would cancel out with that, and I'd have my delta y squared. Now, change in x is going to be positive here, so I can actually bring this outside of the square root sign. So this becomes 1 plus delta y over delta x squared times delta x. So that's just the length of that one little segment. Well, the idea then is we want to add up. We want to add up all these little lengths together. So this is just the length of one of them. We want to add them all together, and then we want to do the limit as these little segments get smaller and smaller, but we use more of them. So when we add up a whole bunch of tiny little things, well, that's our integral. So essentially what we're doing here is we're taking this length of the kind of the hypotenuse of a right triangle here, a little line segment here, and we're just adding up a whole bunch of those little pieces. And that's where this formula comes from. We have our square root term times dx, and then the integral sign is adding up a whole bunch of tiny little line segments that we're using to kind of make up our curve. All right, so that's a little of the backstory. Let's see a calculation. And we're just going to look at example 1. So we're just going to set up an integral here. So let's look at example 1. We're going to set up the integral that would give the length of the curve y equal to 1/2 x squared, going from the point 0, 0 to the point 2, 2. All right, so let's start by writing our formula down. So the length of a curve is the integral from a to b, square root 1 plus the derivative of y with respect to x squared dx. So there's a few things we have to do. We have to first figure out what are the limits of integration going to be. So in this case, our function here is given in terms of x. So this is, x is kind of the main variable. So in order to get the limits of integration, we have the 2 points that are specified. So let's figure out what the x coordinates are. So we got 0 from the one coordinate for the 1 point, and then 2 from the other point. So those are going to be our limits of integration. We're going to integrate from 0 to 2. And then we also need to know the derivative. So let's calculate our derivative, y prime. And this one's not too bad. We can differentiate this. So if we do a little bit of derivative power rule on that x squared, we end up with 1/2 the constant multiple, and then the derivative of x squared is 2x. So the constant multiple just kind of stays in front, and then our derivative power rule, we bring down the exponent and we subtract 1. So we get 2 minus 1 here. I know we've been doing derivatives. I don't know why I'm explaining it so much. All right. So let's simplify that. So the 2 and the 1/2 cancel, and then we're just left with x. And let's fill that in. And when we do that, we end up with the square root of 1 plus. Now we got to square this derivative. So we're going to take the derivative that we found and square it. And if we clean that up, get rid of the parentheses, square root of 1 plus x squared. All right. So this one is just setting up the integral. And this is kind of a preview of things to come. We're going to get into more integration techniques. So at this point, this is not something that we haven't learned the technique on how to do this. So square root functions are notoriously kind of tricky to integrate. And this is one of those things where we actually can't do this one yet. All right, so that's going to do it for today's prep. And in class, we're going to look at example 2. So if you want to, give this one a little try, set it up. This one you should be able to integrate, though, once you do it. So, but we'll try this one out in class. So we'll see you then. Bye-bye.